All right, so what I've been asked to do by Vikki, who I'll introduce in a moment, is show you some slides that Richard took, because he showed them to her and she said, you have to share those first. So from current slides. So back in March of 2001, when Richard Corbett lived up there, he noticed this sky lighting up with aurora, and he went out using a Kodachrome and SLR with a 50mm lens and a 3-second exposure on a tripod, and he got this and that and that. And he says this is an hour later. Everything had changed to orange and green by this time, and the shot looked southeast with his house and his neighbors visible, as well as a jet contrail. And I understand he invited the woman who ultimately became his wife to come and view this with him, and I think that was part of the reason they ended up getting together.
So today we will talk about the phenomena of the northern and southern lights, and we're providing some scientific terms and practical advices about auroras, how to observe the auroras, and we will also talk about space weather. Specifically, we'll mention the solar activities and their effects on us people, and on the Earth, the planet Earth. We'll also mention about the Earth's magnetosphere and what happens in the magnetosphere, why we can see auroras, and how we can predict the auroras. And we'll also show you lots of beautiful pictures and videos, and hope the technology will be with us about that. So, have you heard any misconceptions of the auroras? There are some that's on the screen. So some believe that sunlight reflects it off from the polar ice cap. Someone thinks that the moonlight reflects it off of ice crystals in the atmosphere. Some believe that it is caused by electrons that arrive directly from the sun, and those electrons just enter the magnetic field, and the aurora is shown. It's much more to that than that. And some believe that auroras occur only in the winter. So when there is snow, there is auroras. People believe that. And also I noticed one thing in the Yukon. Many people took images and they said, oh, it's the aurora, but actually that was the light pollution of Whitehorse. And other people took pictures and they say, oh, these are auroras, but they were actually light pillars that are visible in cold, foggy days, during cold, foggy days. So I just would like to show you this video. I hope everybody will hear it, and please thumb down if you don't hear it, thumb up if you hear it. Thank you. So wondering how they have been created, how high they are in the sky really, and what kind of processes are happening when these beautiful auroras appear. When in the north we go out observing for galaxies and deep sky, and the auroras appear, sometimes we are mad at auroras, we cannot do astronomy, but then we start to just be immersed in the beautiful views of the auroras. So we saw these auroras, and when we talk about it, we definitely need to talk about weather. So most of us, when we talk about weather, it's in the Earth's atmosphere, but the activity on the surface and in the atmosphere of the sun also creates its own dramatic events that greatly affects us in many different ways. Solar activity is the one that basically helps creating the aurora around the Earth's poles, but it's not only create these spectacular events, but also creates all kinds of troubles. Not the aurora itself, but the energies that the sun sends to us. It causes troubles in the electric grid, communication system, satellites, manned spacecraft, etc. So if you want to know why we can see the auroras and understand, why they are spectacular, we also need to see about the so-called space weather. And to look into space weather, first let's consider to talk about Earth's magnetosphere. So the magnetosphere is basically the area, it's a magnetic area that surrounds the Earth. I think all of you know that the Earth is a bipole, which consists of a northern pole and a southern pole, just because of the internal activities around the core and magma inside the Earth itself. There is a magnetic field has been created, and this magnetic field is about 11 degrees off from the Earth's axis, a rotation axis, if I say it well, and this magnetic field extend out to the interplanetary space pretty far, even beyond the moon. So the shape and the size of the magnetic field is continuously changing, buffeted by the solar wind. And we will talk about the solar wind in really soon. After several centuries of investigation, basically now we know that the Earth's magnetic field is quite complex, and still it can be viewed as a dipole, so that just mentioned. And in 1951, while people were studying why comet tails always point away from the sun, there is a person called Ludwig Biermann who discovered that the sun emits solar wind. He discovered solar wind, basically. And what the solar wind constitutes of is plasma, electrons, yes, but also protons, and also alpha particles that are basically it's a type of helium. And when these particles interact with the Earth's magnetic field, lots of things happen. But let's go back first to the sun and the sun's surface and what happens on the sun, so that we can understand more why this solar wind also comes and what other things can come from the sun. So I am sure many of you have seen sunspots. So sunspots, as you can see, these darker spots on the yellow surface, or enlarge these darker areas called umbra, and a little bit of more orangey area around the black dark umbra is penumbra. So the sunspots are darker compared to the sun's surface Why? Because their temperature is lower. And why the temperature is lower? Because there is magnetic activity is happening there, magnetic flux, magnetic rays or magnetic lines, so-called, they are exiting the sun, and pretty complex way, probably, which I could not tell how, but they are exiting, and that decreases the temperature in those areas. But also we can know that in those areas where the sunspots are happening, there are extended magnetic activity, which also moves the material, the plasma, around the sun's photosphere and chromosphere and up further. So basically, when sunspots basically occur over regions of intense magnetic activity, and when that energy is released out, many things can happen. There can be solar flares, big storms like coronal mass ejections can erupt from the sunspots. And the sunspots, as you know, has a cycle. It's usually 11 years times 2, so the entire thing probably 11 years plus another 11 years is 22 years. And the sunspots, the number of sunspots observed on the surface of the sun is always changing, but it follows a pattern in this 11 year cycle that okay, it is starts to increase for some years, then it decreases some years, and then it increases again, and it's following this kind of a curve. And believe or not, this is how long history we have of the sunspots observations that you can see on the screen. And there have been observed some minimum periods. One is called Maunder minimum, other one is Dalton minimum, and probably we are in another minimum now. We will see what happens to the coming sunspots cycle, if it starts to come back up or not, but this is the prediction. So we are 2023. This graph was made probably 2022 and a half. So as you see that since 1980, 1990, the number of sunspots visible on the sun are decreasing. And it is also interesting that the sunspot activity is also connected to how strongly, how much, or how many times we can see auroras. So that's why it is also a significant connection to the auroras. So the 11 sunspot cycle is a half of a longer 22-year cycle of solar activity. Each time the sunspot count rises and falls, the magnetic field of the sun associated with sunspots reverses polarity. So the orientation of the magnetic fields in the sun, northern and southern hemisphere switch. Like probably on the Earth, I knew a number long time ago, maybe 30,000 year or 60,000 year. Often the polarity of the southern and the northern pole switches actually. So if we would take a compass out and it's showing north now, if the polarity switches, then the north would be south, the south would be north. But this is happening on the sun every 22 years. So in thermomagnetic fields, the solar cycle is only complete after the two 11-year sunspot cycles. So basically it's 22 years. I would like to mention about the 10.7 centimeter radial flux as well, because the solar radial flux 10.7 centimeter, which is, I'm reading it, 2800 megahertz. If somebody knows about frequencies, it is an excellent indicator of solar activity. And why it is really nice to measure this one, because one, it's Canadian. We can measure it in Penticton at the how do you call it, the at the Solar Observatory near Penticton, and you can measure it during clouds. You can measure it when it's sunny. And basically, this radio emission originates high in the chromosphere of the sun and the low in the corona of the sun. And it correlates well with the sunspot numbers, I will show in a second, and as well as the number of ultraviolet and visible solar irradiance records, which are basically energy, surface energies, watt per square meter probably, which is measured up in the higher atmosphere or maybe even out in the space, not sure. So let's say that these are so at 1 astronomical units away from the sun, at this 10.7 centimeter radio flux, you can see the purple and black diagram on the top, which showing the solar fluxes between 50 and about 350 flux units from 1945 to 2005. And if you compare it with the sunspots number that is below, that's totally correlates or at least pretty close to it. So that's a really good indication about solar cycles, sunspot numbers, and solar activity that basically is at the Earth's distance, which is 1 astronomical unit. So, and it is not only just to measure it for fun to see that it correlates with the sunspots, but it's also very valuable specifying and forecasting the space weather itself. And because it's a long record, it provides climatology of solar activity over 6 solar cycles by now. So if we look at this one, basically it's a little bit complicated for me, but the main thing is that there is a so-called EUV, which is extreme ultraviolet emission, that impacts the ionosphere, which is the higher atmosphere of the Earth, and modify the upper atmosphere track well within this 10.7 index. So why it is important? Because these ultraviolet emissions, they also impact communication and radio frequencies. So they also affect stratosphere and ozone layer as well. Okay, try to get the next one. So let's quickly get into the Earth's magnetosphere. So you see on the left side of the screen there is the sun, and those lines are basically just illustration of the solar wind, which solar wind is hitting the Earth's magnetosphere. So when the atoms and parts of atoms leave the sun at enormous speeds, basically it's almost about 1 million miles per hour. So this material flow is called a solar wind, and it basically out from the sun extends to every direction. So it's not only going towards the Earth, it's going to every planet, it's like a globe of streams that streams out from the sun. And as it moves through the entire solar system, some of the streams hit the Earth. So most of the solar wind is made of the charged particles, protons, electrons, alpha particles, which are the nuclei of the helium atoms. So basically, they are stripped down helium atoms because of the processes of the sun. And so when the charged particles reach our planet, they are caught up in a magnetic zone around the Earth and spiral around it. And this magnetic zone is called magnetosphere. A part of it, it's visible here, and we'll see the next slide more. And the magnetosphere around the Earth basically keeps most of these charged particles from reaching us and making life possible on the planet. So basically, there is this kind of magnetosphere that where these solar winds are piling up like I don't know, like as if it would be a pillow holding in front of the Earth, and nothing can hit the Earth. But of course, much of the solar wind goes through, but they are captured by the magnetic. Where is that slide that I wanted to show? By the magnetic field. Maybe I go back. So you can see the Earth, and you can see this yellow and purple lines around the Earth, which represent the magnetic flux lines around the Earth. And basically, if we go here, the boundary between the solar wind and the Earth's magnetic field is called magnetopause. The boundary constantly is in motion as the Earth is buffeted by the solar wind. So while magnetopause shields some extent, it's far from impenetrable, and energy, mass, and momentum are transferred from the solar wind regions inside the Earth's magnetosphere. So, basically, the interaction between the solar wind and the Earth's magnetic field and the influence of the underlying atmosphere and ionosphere creates various regions of fields, plasmas, currents inside magnetosphere. Conditions inside the magnetosphere highly dynamic and create what we call space weather, and as mentioned, affects the technological systems and human activities. Now, there are so-called ring currents. This is the Birkeland ring currents. So basically, the movement of charged particles in the Earth's magnetic field produces very powerful hypersonic electric currents, electromagnetic currents actually, from the ionosphere to the upper atmosphere to the magnetic field. And it is called Birkeland currents because Birkeland discovered it. And what is really interesting about these currents, that they can carry about 1 terawatt electric power to the upper atmosphere. So it is about 30 times the energy consumed in New York during a heat wave by the air conditioning. So Birkeland determined in 1908 that large-scale ionospheric field aligned currents, they were associated with the visible auroras. So if you are a scientist, you can definitely look into that. I'm not really a scientist, but I love popular astronomy. And it was really interesting to read about it and how powerful these electric currents are, and basically they contribute to the creation of the auroras. Let's go back to the sun a little bit and see that in addition to the steady solar wind, the sun also has occasional storms in the upper layers. I hope everybody can understand my accent. I have some accent. So these storms are the result of sudden release of a lot of magnetic energy, basically that erupt out from sunspots, but sometimes it can also erupt out from areas that obviously looked kind of quiet before. And these solar storms, they can fling out enormous amount of material out to the space, and if this material is basically the trajectory is towards the Earth, then Earth communications, pipelines, electric grid, everything can be in really big trouble. And this is one reason, and I will mention that maybe a little bit later on. This is one reason that there are satellites out measuring the sun's activity 24 hours a day, and basically there is an alert system to the electrical grid, to the pipelines, to the communications, all kinds of communication systems, so that they can do the proper precautions. So prominences and filaments. So there are three main types of solar storms. One is solar flares. There are coronal mass ejections and solar radiation storms. So again, solar flare, coronal mass ejection, and solar radiation storm. So when we talk about prominences, filaments, basically they are in the category or subcategory of solar flares. So these prominences are large, bright features. They are extending out from the sun's photosphere. Prominences are anchored to the sun's surface in the photosphere and extend outwards to the hotter outer atmosphere called the corona of the sun. So prominences can develop through days, and they can even stay active for months. There are more stable prominences. There are prominences that they don't last too. So the red glowing looped material is plasma. It is a hot gas comprised of electrically charged hydrogen and helium, which is what the sun is made of, hydrogen and helium. The prominence plasma flows along a tangled twisted structure of magnetic fields generated by the sun's internal dynamo. And if these prominences are towards us, very often we might see actually that where it touches the sun's photosphere, basically there are sunspots too. Now I would like to show you this video. I hope it starts. It's really beautiful. Can you tell me if you hear it? I can stop it now because the time is a little bit shorter. I hope I can stop it. Okay, so this is really beautiful. You can find online many videos of prominences. They are just beautiful. So when solar flares occur, when these prominences break up and eject material out of the space, and the solar flares are large outbursts of electric radiation from the sun, which are lasting from minutes to hours. So they are caused by those large scale eruptions. And okay, let's go. Um, and solar flares occur large range of strengths and are classified in a logarithmic scale based on their intensity as by the National Oceanic and Atmospheric Administration. So basically, these solar flares can cause radio blackouts, and as you can see, from minor to extreme, these are classified, and X-ray flare from M1, M5 to X20, which is the most severe radio blackout that can happen globally. And let's go to the coronal mass ejections. So coronal mass ejections are huge explosions of magnetic field and plasma from the sun's corona. When these so-called CMEs or coronal mass ejections occur, they impact the Earth's magnetosphere and causing geomagnetic storms and enhanced auroras. Um, so we are not going into the details of the coronal mass ejections, but when these happen, when these occur, the aurora activities are very, very strong, usually, and even I think a couple of weeks ago, that coronal mass ejection that occurred, they could even observe the aurora in Texas and Florida. So, but let's see what happened in the Yukon in 2012. One of our members
so imagine looking up in the sky and seeing this.
Created this
For real.
photo.
Oh my gosh, it happened just the other day. It's the result of something being called mind-bogglingly gorgeous. Our Josh Les is here with the story behind this. And that's pretty amazing. It almost looks so amazing that it's fake.
Well, I know this actually looks fake, and we're going to lead to the brand new video that NASA gave me. But let me give you the story behind this, because this is an aurora. But it begins, the story of this amazing image begins with the sun. So let's go to the sun. Here's what this is. It all begins with a solar flare. So basically, what we have here from NASA, this is so unusual to have a shot like that. Look at that.
Wow.
The sun basically pushed out this mass of plasma that's huge. And as you watch that bit that goes out, I want everyone to understand how massive it is. NASA tells me this. It's called a coronal mass ejection, 30 times the width of Earth. After that solar ejection goes flying through the sky, what happens is it can take a few different paths, and sometimes it can take a few days. And in this case, it took 3 days before it got into the area where Earth is, and our Earth can reject it, can push it back. And when the Earth mixes with that solar flare, what you get is those amazing colors.
Wow.
Right? So our magnetic field
Beautiful.
matches it. And this right here, brand new, NASA sent this
These are
to
incredible
me.
images.
Brand new. No one's seen these before. These are from NASA. And what we're seeing here is 4 different views of the sun having that moment when that solar flare happens. And the reason it's so important is people want to know, our scientists want to understand it, because these can have a huge impact on Earth. By the way, it's the Register in Britain that called this mind-bogglingly gorgeous, which it kind of is. And I want everyone to understand how important this is. So here's a little clip from a NASA scientist explaining how critical this is.
This is billions of tons of material moving at millions of miles an hour. And when those events are directed towards us, they can impact the Earth, they can cause aurora, they can cause technological disturbances, problems with power grids, communication. So fortunately, we have this really amazing, never before seen imagery that allows us to study these events in great detail.
So thanks to Alex Young for that. And these pictures are from a photographer named David Cartier, who was in along the Yukon River in Canada, happened to be out there, captured these pictures. And he tells me each shot is about 5 to 10 seconds worth of what he saw. So it really did look like this to him.
And I was gonna say, it really does look like this by the naked eye. It's not that the result of his film or his, digital imagery
I asked him, I
imposed
said,
these colors.
I was wondering, like, did you do something to take an hour to look like this? He said, no, the exposure was just 5 to 10 seconds on each one.
Okay, so
All right.
okay, so basically, it is really interesting that this coronal mass ejection was recorded by SOHO, which is a satellite is somewhere towards the sun, and also actually somebody on the Earth at the same time made a picture of it, and it happened to be a friend and member of RASC in the Yukon. And also I didn't find that image, but of the same aurora actually was also captured from the International Space Station. So, but let's continue the solar radiation storm with the solar radiation storm. So the NOAA also categorizes a solar radiation storm because basically it occurs when a large-scale magnetic eruption, often a coronal mass ejection, and associated solar flare occurs that accelerates charged particles with very high velocities, like so high that actually the light, 300,000 kilometers per second, it arrives from the sun to Earth. How long? 8 minutes. Now, these solar radiation storms, they can travel 1/3 of the light and can hit the Earth or any other planet in the solar system basically pretty fast. So let's say if it's 8 minutes times 3, 24 minutes, let's say to a few hours, that's how fast those particles are, and they cause extreme they can cause extreme problems. Like how extreme? Let's see S5, like biological unavoidable high radiation hazard to astronauts on extravehicular activity. I think there's a spacewalk. Passengers and crew in high-flying aircraft at high latitudes may be exposed to radiation risk. Satellites may be rendered useless. Memory impacts can cause loss of control, cause serious noise in image data. Star trackers may be unable to locate sources. Permanent damage to solar panels is possible. So it can incapacitate basically many satellites. Other systems, complete blackout of high-frequency radio communications through the polar regions, and position errors in the navigation operations can occur. So these are pretty serious consequences if a solar radiation storm hits the Earth. So oops, can I? Okay. So there are geomagnetic effects as well. Geomagnetic storming with the associated aurora display, and geomagnetically induced currents in the ground. So what we have in the grounds, internet cables, we have pipelines, and these are affected, and actually these how to say, service providers are prepared for geomagnetic effects to save their own system. So prediction is really important for us. So I just would like to show you a short video, of beautiful auroras, maybe just even half of it. I stop it now. Is it okay if I stop it? Don't run out of time? Okay, thank you so much. This is really beautiful. It's just so wonderful to see these time-lapse videos and seeing the all different kind of colors of auroras. And we'll, okay. And we'll also talk about why are the auroras colorful and what causes the colors. But first, let's see how we predict the auroras. So the satellites that are monitoring the sun are SDO, SOHO, and others that are observing the sun 24 hours a day. And they are measuring the speed of the solar wind outside the Earth's magnetosphere with an ACE spacecraft. And also a K-index is being created by the so-called horizontal component of Earth's magnetic field with integer in the range of 0 to 9, with 1 being calm and 5 or more are indicating a geomagnetic storm. Now, the K-index is not that we use for our aurora prediction, but we use the planetary KP index that you might all be very familiar with, because if you download an Aurora app on your cell phones, KP index will show. And this is basically a planetary 3-hour range index, and the mean standardized K index, which is mentioned before, from 13 geomagnetic observatories between 44 and 60 degrees northern or southern geomagnetic latitude. But I also know there is one in Fairbanks, so it's pretty high latitude. Kp is an excellent indicator of disturbances in the Earth's magnetic field, and basically used to decide whether the geomagnetic alerts or warnings needs to be issued for service providers and users who are affected by it. Civil, army, communications, pipelines, electrical grids, astronauts in space, satellites, NASA. So, NOAA using a geomagnetic storm activity scale, which is correlated to the KP number. It's a G scale, G0 to 5. And this is how you can see an aurora prediction on your cell phone. Probably you can. And usually if it's stronger than 3, you can expect stronger auroras that you can see on southern latitudes as well. Here in the Yukon, or people who live under the aurora oval, we often see auroras even when the Kp index is, let's say, 1 or 2 or 3, just because the aurora oval is very near to us. But let's go, before talking more about aurora oval, let's see why auroras have different colors and where the aurora appears. So aurora usually appears in the height of 100 to 400 kilometers. So it's really the high, really high away from the Earth's surface. Electrons and other particles too, not only electrons, hit the air molecules, and the molecules are getting excited. It means that the oxygen, hydrogen, nitrogen, carbon, and other molecules have or atoms, they have electrons that are going around those protons, and those electrons are lifted up to a higher energy orbit, but they cannot stay there, and when they jump back, this is when light emits. And based on what atom or molecule the solar wind material or coronal mass ejection material, solar flare material hits. Depending on that, the colors are different. And I wrote it down here for you so that you can remember it more than just me saying it. So you can see that the International Space Station is at about 400 kilometers high. The red auroras a little bit lower than that, green auroras lower, the blue auroras even lower. And it is interesting that the auroras appear higher when compared to when meteors light up in the atmosphere. And as you can see, an ozone layer is even way lower than that. And it's really, and the height of the aurora is really far away from commercial airliners' altitudes. So oxygen emits greenish yellowish light or a red light. Nitrogen gives off blue light, and blending these one can produce mixed colors, purples, pinks, oranges, whites. But let's say green is oxygen up to 240 kilometers, red oxygen above 240 kilometers, blue nitrogen up to 80 kilometers in altitude, so that's the lower one a little bit, and purple violet nitrogen above 80 kilometers in altitude. So let's see some pictures. These are red auroras, beautiful. It's somewhere in Alaska at St. Elias Mountain. And you can see there are blue, purple, green, all kinds of colors of auroras. These are green auroras. Here in Whitehorse, we see lots of greens, lots of green auroras. But I also all kinds of colors. So I also saw like this radiating from the zenith every way like this. I saw this kind of auroras too, all kinds of lights. And actually, when this one happens, this is also called actually break point, I think. One of the next slide will show it. It's a break point, and it has a little bit of significance. And you can see Pleiades above, beautiful auroras of purplish, reddish, and greenish colors, and a satellite is running through. And then another one. And this is also a video. Let's see how long. Hope it's not very long. Let's play it. We can see different. It's just 2 minutes. Let's play it. So it's very typical that it goes like a curtain. And the red appears. Okay, so I just like to show these ones because it gives us a nice break and some you know, that it's beautiful. So let's see if I can get to the next screen. Next screen. Oops, what's happening? Okay, got it. So the title is it Aurora? No, Steve, it's not. So anybody knows what is Steve? Basically, Steve is discovered by Albertan amateur astronomers, basically citizen scientists, by being diligent and observant about what happens in the nature. And basically what Steve is, it's a so-called SAID, S-A-I-D, SAID, which is a sub-auroral ion drift. It is also known, other words, as I can't spell it out, polarization jet. It's an atmospheric phenomenon driven by substorms in the Earth's magnetosphere. So first, the SAID, this sub-auroral substorm, ion drifts, discovered in 1971. It is a latitudinally narrow layer of rapid westward flowing ions in Earth's ionosphere. So it's charged, right? Because it's in the ionosphere. Though not traditionally associated with the optical emission of these purple strays, the Steve discovery paper suggested the link between the two. And then they were observed, the SED were observed for many hours, equatorward of the auroral zone at sub-auroral latitudes. And these ones can be observed about 6 p.m. to 10 p.m. usually. They can occur individually and as multiple events too. So it is characterized by a reduced density of ions. Ions mean that they are charged particles, either plus or minus, a strong westward flow, and an increased temperature. And they can last between 30 minutes to about 3 hours. And also have been studied for decades. The former discovery of Steve and SED never been associated with optical emissions before. So it is a new thing that scientists can study and figure out what's really happening. The next one. Okay, so you can see it is also Steve, that purple stray. Okay, is it aurora? No, dunes. They are dunes. What are dunes? The dunes are rare atmospheric gravity waves called mesospheric bores. I don't understand scientifically what are mesospheric bores, but they are kind of gravity waves. And they occur when a gravity wave that's rising up in the atmosphere becomes bent and sandwiched between two colder layers of atmosphere. The inversion layer, so it's two layers of atmosphere, mesopause and inversion layer. So these gravity waves just somehow get trapped there and probably make dunes there. So when the electrons from the sun stream in, the folds with higher oxygen levels light up more than the places lacking in oxygen, creating characteristic stripes. So here is a video of the dunes. So the dunes are the ones that are coming towards the left side of the screen in kind of layers, and below that are the auroras swirling. Okay. Okay, and let's talk about the aurora oval just for a second. So basically, this image is from the International Space Station by an astronaut. When a solar storm occurred, he took the pictures. I'm really sure the aurora oval is there too. The aurora oval basically is always there. It is always surrounding the northern pole and the southern pole, and it's always glowing green. Glowing green. So when the solar wind is calm and sunspots are small, the aurora can only be seen at high altitudes and might be faint, but there is still aurora. And in order to see the aurora, the sky must be dark and clear because those are faint. If sunlight and clouds are the biggest obstacles to see that. So you can also look at the aurora oval from an airplane seen by the picture beside it, traveling above the clouds 36,000 feet high. So if you come to Erik Nilsson Airport to Whitehorse and you take airplane to Yellowknife or go up to Inuvik or Old Crow or Dawson City and it appears to be at nighttime, or Whitehorse had an aurora charter too, then you can certainly see auroras. And we are Canadians, maybe even if you just from Vancouver you fly to Toronto at night and you sit on the left side of the airplane, you might just see auroras. But where is best to see it? Of course, the Yukon and other Canadian provinces and territories too, well positioned. So the permanent aurora oval covers almost the entire Yukon, and I recommend to go a little bit northern than Whitehorse, especially Tombstone National Park, Dawson City, those areas, Inuvik, those that's also already Northwest Territories. Those are amazing places to watch auroras. And I wrote this down because it is really difficult to remember word to word, and you might be able to also make a note or take a picture of it yourself so that you can remember. So when we can see auroras and when we can't. So when the solar wind is perturbed by recent flare or other event on the sun, we might see auroras. So after the solar wind transfer lots of energy into the magnetosphere, and of course all the materials builds up tension, they cause explosive auroral display. And these are called substorms. So the substorm starts with a slow expansion of the aurora oval, followed by a sudden brightening of a small spot called auroral breakup. That's what I mentioned, auroral breakup. So this spot is usually near the place of the aurora oval that is the opposite side of the sun, which means it's midnight. Okay, so the auroral breakup occurs around midnight, and the brightening rapidly grows until the entire auroral oval is affected. An observer on the ground where this breakup occurs, you can see the aurora other places as well, but where this breakup occurs, you see a sudden brightening of the aurora, which fills almost the entire sky within seconds. And then after that, the aurora will be a shape of rapidly moving curtains. If you are under the aurora oval, west of this breakup, so let's say it was midnight, right? So if you are west of this breakup, it means it's before midnight. You will see a bright aurora moving towards you from the east, and that might cover almost the entire sky and move from eastern to western horizon within minutes. This often looks like a huge spiral of curtains with many smaller curves within the curtains. And after this subsides, the sky might be filled with the diffuse patches of aurora that turns on and off. Sometimes you just see it like a haziness, you don't even see colors, but sometimes you do. So this whole substorm typically lasts between 30 and 90 minutes. And during periods of high solar activity, we can see it multiple times during the night. Which months, years are best for aurora? So appearance of northern lights is very difficult to predict. You cannot really know more than 3 hours sometimes before it happens. The aurora activities, the KP index, basically predicts for 3 days in advance, because that's how fast the solar wind travels and can see, solar flares. Of course, when we see more sunspots, when there is solar maximum, as you remember of the curve was the solar cycle, the maximum where there are more sunspots occur, you can see more auroras. And by observers' experience, aurora borealis, and actually australis too, because it's kind of the other side of the pole, we remain very active for 2 or 3 years either side of the solar maximum. So there is no definitive research to suggest that any particular time of the year is better chance or not. It can occur throughout the year, But during the summer, of course, it's more invisible to the eye because of the sun. So this is also a misconception that, as I said, that aurora is only during the winter. No, it also appears during the summer, daytime, just we can't really see it. So if we have a few more minutes, do we have a few more minutes? Okay, thank you. So basically, let's see the seasons, the months. So what are chances and opportunities to see auroras between January and March? So most popular months for aurora hunting are the long dark nights and the winter. But it's very cold and very dark. But it is said that the aurora is more likely appear on colder nights. So perhaps if you are up to the cold, you can try. February and March, the temperatures begin to rise, although it can still get pretty cold at night, and less snow clouds overhead can help us to see aurora more often. It is a speculation that spring and autumn equinoxes might bring greater solar activity. And if you combine it with a little bit of warmer temperatures and improving weather, you may feel compelled to be outside at night for a little bit longer. Between April and August, well, this is when there are auroras for sure, but here in the north midnight sun, it is impossible to see the northern lights, except when there is dusk and you can see kind of a whitish cloud-like features that are auroras, and if you have good eyes you can say, yeah, I know it's aurora. September, October, these are really good months for watching auroras, observing them, because it's not yet extremely cold usually, and the colors of the forest and mountains are absolutely magical. The waters are not frozen, so you can take images like that in the background where the aurora reflects back from the waters. November and December, these are really good months for auroras, but they are really cold too. Permanent snow, and the snow brings quite a bit of cloud cover, but the shorter days bring darker skies, which increases the amount of time while the aurora might be visible. So what time of the day? Well, it's difficult to say, but there are all kinds of beliefs. But optimum time seems to be between 9:30 p.m. to 1 a.m. And ultimately, the secret to seeing the aurora borealis is patience. Let's say if you come up to the north and you are in a snowmobile or minibus or snowshoes, search is unsuccessful, then it's very often if you brave the cold night rather than those who stay by beautiful long, beautiful warm fireplaces. So you will have more chances to see if you have the endurance to stay out a little bit longer those really cold days. Can I close it with a video?
Sure.
And this video was made in the Yukon. Okay, sorry, I just replied. Okay, let's see if it has volume. Okay. There's the Yukon River. I think my connection is a little bit. So thank you so much. This would be the presentation about the Northern Lights. Thank you so much for listening and appreciate your attention. Any
Thank you.
questions from anyone?
I haven't seen any yet,
Thank
but
you.
while we're waiting to see if someone throws one in, somebody actually put Steve, 3 question marks. The name comes from the Aurora chasers in Alberta, and they were meeting with scientists at the University of Calgary, talking about that phenomenon. And they didn't know what to call it. And Greg Ratzlaff, who was one of their major Aurora chasers, had just watched an animated movie where some scary creature on the other side of the hedge that nobody knew what it was. They figured, well, we'll name it and it'll be safer. So they called it Steve. And he said, you know what? Let's call it Steve.
Mhm.
And it's stuck.
It's
They
stuck,
actually
that's
turned
right.
it into an acronym that means something, and I don't pretend to remember what it is because it's gone through several different versions. But if you look it up, they actually have turned it into an acronym now. But that's the true story of how it got the name Steve.
Oh, nice, nice. Thank you for sharing that.
That was wonderful.
Yeah, thank you so much. Thank you, everybody.
Yeah, thank you. One question for you, Vikki.
Yes.
You mentioned you can see auroras in the north during the summer. I took a whole lot of pictures when I lived up there of noctilucent clouds.
I saw those clouds too, couple of times, maybe not many times, but I saw them a few times, and they are absolutely amazing to see.
Yeah. And they're up there shining in the sunlight at 2 o'clock in the morning, which is local midnight. Solar.
Yes. And I think they are very high altitude clouds, right?
Yeah, 60 to 90 kilometers.
Wow.
Apparently they're formed water vapor that leaks into the mesosphere slowly, nucleates on the dust that's left behind from vaporizing meteors.
Wow.
That's the nucleation sites up there. And I just thought it was really cool. I saw them first about 40 years ago west of Calgary, and I had to stop the car. I didn't know what the hell I was seeing.
Yes.
But the Yukon is a terrific place. I will dig through my archives of pictures and see what I can find. I can send them to you.
Oh, sure. Please, please.
Okay.
Yeah, you can share them with all of us, Richard.
Oh, yes.
Thank you.